Welcome to this lecture series in coordinate geometry. In this lecture, we'll look at the equations of multiple straight lines. We will define what that means and let us recall what we need. So of course, we will need to know what is meant by the equation of a line. We need to know this one fact at a certain point, that the product of roots of a polynomial of this sort where an is non-zero, so it's a degree n polynomial, so then the product of all the roots including the complex roots is minus a naught divided by an. So this is just it's not a hard fact or anything, but we will use it at one point. Okay, we will need the notion of the union of two sets. So suppose A and B are two sets, and if we are talking in terms of Venn diagrams, then let's say A and B are these two sets, then the union of A and B is all the points that have been shaded. Okay, formally the union of two sets A and B is the collection of all the points which are either in A or in B or in both. So that's the notion of union of two sets. We will use it. Okay. So here are some problems for practice. And now let us get started. So first we will look at zero sets. I don't think this phraseology occurs in high school textbooks, but it is a very simple thing. So let this be an algebraic expression. So this means algebraic, and yeah. So let's not try to formally define what is an algebraic expression, which is why I have put it in brackets. But when I say algebraic expression, I mean things of this sort, like x square plus y square minus 2. This is an algebraic expression in x and y. Or 2x cubed minus 3y square plus xy minus 7. This is an algebraic expression. Or more simply, 2x plus 3y minus 5. This is an algebraic expression in x and y. So I'm sure we understand what is an algebraic expression. Formally, what I mean is a polynomial in two variables. But I'm sure we anyway understand, at least intuitively, what is an algebraic expression in two variables. Okay. So once we have such an algebraic expression, the zero set of this guy, if you want, you can write fx comma y, is defined as the set of all the points a comma b in the plane, in the Cartesian plane, such that this is 0. So when we write this, we just mean substitute a in place of x and b in place of y. A and b are real numbers. And if this is 0, we say that this point, this is an ordered pair. So this is the abscissa, this is the ordinate. So if this happens, then we say that this is in the zero set of this guy. The terminology is very natural. Anything that makes this 0 is in the zero set. Okay. I think I have taken examples. Yeah. So here is an example, but perhaps before we look at an example, we should establish the notation for it. So the zero set of fx comma y will be denoted by this notation. Okay, that will be the notation for the zero set. Now here is a very, very simple example. You take fx comma y as this algebraic expression. Then what is the zero set? The zero set is all those points where the abscissa is equal to the ordinate, because the zero set is basically solving this. What are all the ordered pairs x and y where this happens? It is these points, the points which lie on this line. So a line, straight line in the coordinate plane is after all a zero set of things of this sort, ax plus by plus c. This is an algebraic expression. If not both of A and B are 0, then the 0 set is a line, and precisely those are the lines. Okay. Here is another example. This time our algebraic expression is a little bit more complicated, and if you plot all the points where this vanishes, you will see something like that. Here is another example. We have something that is degree 2. So here the exponents are there. So this is something. And if you look at the 0 set of this, what you're asking is, when does this become true? For what points x and y, x comma y, does this happen? But if you interpret this as the distance from the origin or the square of the distance from the origin, then all we are asking is, what are all the points whose distance from the origin is, or the square of the distance from the origin is 1, which is same as asking the distance from the origin being equal to 1. And therefore, it is this set of points. All the points lying on this circle, which is of radius 1 and centered at the origin. So 3 very simple examples illustrating the concept of the 0 set. Okay. Now, suppose we have two algebraic expressions f and g, and we define a third one by taking the product. So algebraic expressions can be multiplied. Surely you are able to multiply things like this. Something, I'm just writing some random thing. Of course, you can multiply by opening the bracket like we do in primary school. So that's the kind of thing that is meant by h, x, comma, y. So then the 0 set of h, x, comma, y, well, we have already defined the 0 sets. This is the product of two algebraic expressions is again an algebraic expression. So the 0 set of h, x, comma, y is now a well-defined thing, but what we want to say is that the 0 set of h, x, comma, y is the union of the 0 set of f and the 0 set of g. It's a very, very simple fact. Sorry, I meant to write union. I haven't written it. Yeah. So it's the union of these two things. This is a subset of the plane. This is a subset of the plane. We are just taking the union, and we discussed the meaning of the union in the beginning of this lecture. So why is this? It's a very, very straightforward thing. So first of all, if let me use a comma b. Suppose a comma b lies in the 0 set of f, then by definition this is 0, and hence maybe I should use a different color for this. And hence this product is also 0, which means this is 0 by definition of h, which means this point a comma b lies in the 0 set of h, right? So if you have something in the 0 set of f, then it lies in the 0 set of h. Similarly, if you have something in the 0 set of g, it will also lie in the 0 set of h. So what we have shown so far is that 0 set of f as well as the 0 set of g are both contained in the 0 set of h, which means the union of the 0 sets, and let me be a little bit lazy, I will not write fx comma y, I will just write f. So the union of the 0 sets is contained in the 0 set of h. So if you have a subset contained in something and another subset contained in the same thing, their union will be contained in the same thing. So that's what we are using. So this containment is there. This is the notation for containment. Perhaps I should have said it. So when we make this symbol, we mean that every element of this guy is here. And yeah, so this is the notation for subset. Okay, so what we see is that this is the case. And for the reverse containment, once we establish the reverse containment, then this equality will be established. So for the reverse containment, suppose h a comma b is 0 for some a and b. Then either f a comma b must be 0 or g a comma b must be 0, and hence a comma b must lie either in the 0 set of f or in the 0 set of g or in both. So this reverse containment will also follow, and hence this is true. So this is a very simple deduction, and one can generalize this to multiple algebraic expressions. Suppose we have n algebraic expressions, then defining h as the product of all these implies that the 0 set of h is the union of the 0 sets of all of them. Okay, so just a very simple extension of this thing which happened for two algebraic expressions. If you want to prove this formally, you can use induction on this one. Anyway, so now we can go to pairs of straight lines. Suppose we have two straight lines, L1 and L2 in the plane, given by these two equations. Then is there some algebraic expression that we can write down to express this union? So this cross thing is a subset of the plane. Can we nail it down using an algebraic expression? Of course we can, because by what we learned, so first of all, before we write down the expression, note that the line L1 is nothing but the 0 set of this expression, right? And L2 is nothing but the 0 set of this guy. That's what it means to say that L1 is this line. And therefore, by what we learned, L1 union L2 is the 0 set of the product of the two algebraic expressions. Right? This is what we just learned. And therefore, the union of L1 and L2, meaning that thing, is given by this equation, which is this. So the set of points on the plane which make this 0 are precisely the points on the union of L1 and L2. So this shape is expressed by this algebraic expression. Okay, I hope that was clear. Now one can generalize the previous thing to not just 2 but n straight lines. So each Li is suppose given by this equation. Then the union of all of them is given by the following. Just take the product of all of these algebraic expressions and equate it to 0. Just a very simple extension of the previous slide.